Hey, once again. So I was going to do a written answer key for the probability questions, but I thought it might be better to do a quick little video because there was something I didn't put in the other video about complementary events. So here we go. So this might be better for you. Plus, maybe the way I explain it might be better too if you can hear how I'm saying it here. So these are the questions 1 to 10 on the last homework assignment. And I've actually done most of the answers here, so I'm going to scroll through them pretty quickly here. Question number one, it was the probability of getting two girls. So we can see each girl is a 50% chance, or one half. So one half times one half is a quarter, which is equal to 0.25, which is equal to 25%. So we were saying give all three ways of writing it. Question number two, though, I wanted us to spend a little bit of time going through that. And what the question was determine the probability of at least one boy being born. So that means you could have one boy, two boys, or three boys. And so one way to do the question would be to work out the probability of all of those events. And I'm just going to show you on the tree diagram where that would happen here. So I'm going to use a red dot to show that. So this branch is three boys, so that's at least one boy. This is two boys and one girl. This is two boys and one girl. This is one boy and two girls. Girl, boy, boy, girl, boy, girl, and girl, girl, boy. And so you can see there actually would be 7 different calculations to do that kind of problem. So another way to do this problem is what we look at is called the complementary event. And that's basically the event you don't want to answer, that is the one that's not being asked of you, which would be the probability of having 0 boys. So having 0 boys being born. And the only branch that shows 0 boys being born is this one right here. Now, because the probability of having at least one boy is the 7 dots you see at the bottom, and the probability of having 0 boys is the orange arrow, all of those numbers have to add to 100%, or 1, probability of 1. So I'm going to work out this probability first, 0 boys, so all girls. So that would be 1 half times 1 half times 1 half, which is 1/8. So there's a 1/8 chance of having no boys in 3 children. That is all girls, which is low, obviously. And now what I'm going to do is look at the probability of at least one boy. So that would be 1 minus the probability of having 0 boys, because 0 boys is the only group not included in the at least one boy group. So if I take 1 and I minus 1/8, that's of course 8/8 minus 1/8, which is 7/8. And then if we take 7 divided by 8 is 0.875, or about an 87.5% chance of that occurring. So if you have 3 children, the probability of having at least one of the children be a boy is 87.5%. So what I looked at here was doing the calculation for 0 boys, and we call that the complementary event. So complementary, basically the event you weren't really being asked for in the first place. And then we subtracted that from 100, or 1, because that's the chance of all the events occurring. So I'm not going to give you any complementary event questions on the test, but I thought I'd just show you that one where you can actually answer the question quicker in a more indirect way. Question number 3 was the probability getting a 5 on a 10-sided dice and a tails on a coin. And so that was 1/10 times 1/2. These events would be independent of each other. So 1/10 times 1/5 is 1/20. Question B was rolling a number divisible by 3. So on a 10-sided dice, 3, 6, and 9 are all numbers divisible by 3. So there'd be 3 such numbers. So there's 3/10 times 1/2 for the heads. So 3/20. Okay. Once again, if I'm going too quickly, you can just always pause the video or rewind if you're not sure about that. Question number 4 and A and B are pretty straightforward. 5 green marbles, so 5 out of 20. Blue is 6, so 6 out of 20. And then they reduce down to the following. Question C, tree diagram shows that there's a 9 in 20 chance of getting a red, and then a 9 in 20 chance of getting another red, assuming you have what's called replacement here, that you're putting the marble back into the bag. So basically, it just resets the condition again, which kind of makes it like flipping a coin, really. Question D is green and blue. So 5 green marbles, 6 blue marbles. And notice they're both over 20s because you replace the marble again. So 5 out of 20 times 6 out of 20, and you can see the work there. Question E, we're looking at a situation where you're not replacing now. So basically you take a marble out and you don't replace it. So the probability of getting red is 9 out of 20. There's 9 red marbles. And the chance of getting another red would be 8, because remember you took one out. And it would be 8 out of 19 now. And so 9 over 20 times 8 over 19, I believe, gives us the numbers we see there. And once again, if you don't agree with these numbers that I've worked out, please email me and I will change those again. Question F, we're looking at getting the first marble being blue, so 6 out of 20, and the second marble being green. Now there's 5 green marbles, so it's still 5, but notice the number on the bottom is 19, and that's because the first marble picked was blue and it wasn't put back in the bag, so you have 1 less marble. And you might notice these little orange question marks I have on the other side, although you don't really need that to answer this question. But if you go into higher level math, you might be concerned about that, because maybe you do need that information. And the reason we can't answer that is because if you're trying to get the question really is, what is the chance of getting the green marble on the second one? If the first marble wasn't blue, it could be green, which would change that number, but it could have also been the other colored marble, the red marble. So we just don't know what that probability is using a 2-branch tree diagram here. Question number 5 was involving cards, and there's a big thing about what kind of cards are in a deck of cards. So the chance of getting a black card and then a red card, and we were doing this without replacement. So basically you take the card, you do not put that one back in, and you draw another card. So once again, you decrease the pile by 1. So there's 26 black cards divided by 52, and then there would be 26 red cards, but divided by 51 because you didn't put the black card back into the deck. Question number 6 shows with replacement, same question really, black and then red. So 26 divided by 52, and then for the black card, and then for the red card, 26 red cards and also divide by 52 because you put the first card back into the deck. And that you can see that the probability works out to be a bit different here. Actually, I made a mistake here. I just should change that. This should be just 25% there. So I noticed that between question 5 and 6, there's a slight difference here, and that's because you didn't replace the card. Question number 7, getting 2 jacks. There's 4 jacks in a deck, so 4 divided by 52, and I believe this question was also without replacement, so 3 divided by 51 then, because if the first card was a jack, you have 1 less jack, and you also have 1 less card in the deck. And question number 8, we're looking at the first card being a king, so 4 kings, so divide by 52, and then we're looking for 2 cards that are black queens. So the black queens are the clubs and the spades here. So queen of spades, queen of clubs are considered to be black cards. So there'd be 2 of those divided by 51 because you're not replacing. Okay, question 9 is, once again, this is beyond the scope of what I would ask you to do on the test because it is kind of tricky. And was a question of being a face card for the first card and the second card being black. So I did the first part of the question by putting in 3 branches. So face card, and then no face cards that are the red ones. So there'd be 20 of those. No face cards that are the black ones, which would be 20 of those. And there's 12 face cards out of 52. So let's say you don't replace. That means you've got 51 cards now, right? You minus 1 of them. And if the face card you picked, and now you're looking for, let me just double check, make sure I'm doing this right. Ooh, hang on a second, I'm gonna close my window here. Sorry, the neighbor's weed whacking the lawn there. So face cards, Yeah, sorry, I'm going to switch this around here. Actually, I misread the question when I wrote it down here. So I'm going to just erase a few things here and then just start again here. So let me just cover some of these numbers up here. So I want a face card for the first card. And what does it say? Face card's first card. And the second card is a black card. Okay, so I need to be a bit more careful how I set this diagram up. So I get a face cards that are black. Face cards that are red. And then face cards that are red. Sorry about that, guys. Someone was mowing their lawn outside. I wasn't sure whether you guys could hear that background or noise or not. I couldn't hear myself think, actually. Let's start again. So I redid the diagram here looking at face cards that are black, face cards that are red, and then the non-face cards. So there's 12 face cards in the deck, and there's 6 that are red and 6 that are black. So there would be a 6 out of 52 chance of getting a black one, a 6 out of 52 chance of getting a red one. And then if we do 52 minus our 12, there would be a 40 out of 52 chance of getting a non-face card. Now, I need to sort of branch into 3 here because if your face card was black and you didn't put it back in, you would have 1 less black card in the deck. And then if you didn't replace it, you'd also have 1 less card overall in the deck. So this is going to definitely be out of 51. And now remember, you've removed a black face card. And right now there should be, of all the cards, 52, there's 26 black cards and 26 red cards. Okay, now if you've removed one of the black ones, then there would be 25 remaining cards that are black, and there would be 26 cards that are red, because you remember the first card you picked was a black face card. Now, if you picked a red face card, there would be 51 cards in the deck. But if you picked a red face card first, then there should be 26 black face cards. And of course, if you picked a red, there'd only be 25 remaining cards. Now, if you didn't pick a face card, then you would still have to know really whether that card was black or red to make a prediction as terms of the probability of these branches. And so we saw that up in the question above where we have those little orange question marks. But we don't actually need to know that because these outcomes are not part of what we're looking for. So what we're looking for is a face card that's black. Face card, and the second one is black, and then a face card that is red, and a second card being black. Because all we really want to know is a face card for the first one. So it could be red or black. Could be the hearts and the diamonds, or it could be the clubs and the spades. And then the second card has to be one of the cards that is black. So we actually have 2 outcomes here. You can see that would do this. So a probability of actually I rewrote that already up there. So let's just write it equals. So we would have 6 out of 52 multiplied by 25 out of 51. And we add that to the other branch, which would be 6 out of 52 multiplied by 26 out of 51. Okay, so they all have the same denominator. So let's just use our calculator here. So 52 times 51 is 2,652. And then 6 times 25 is 150. And then 6 times 26 is 156. Okay, so we have 306 out of 2,652. That's a bit painful to reduce, so I'm just going to be lazy here. So 306 divided by 2,652 gives us a probability of 0.115 roughly, or 11.5%. Okay, so I'm gonna go double back and check that again, but it looks pretty good to me. I'm gonna also take a look now at the last question, number 10, and that's actually a fairly easy one to answer. It's not gonna be as big as these ones. And the question number 10 just says, which question from numbers 1 to 5 are examples or is an example of an independent event? So independent events are ones in which the first event does not affect the second event. So basically, if you're replacing cards here, the second event's not going to be influenced by that event. So I think the only one that shows that is number 5. So number 5, question number 5, is truly an independent event. All the other ones, well, actually, no, number 6, sorry, number 6. Number 5 says without replacement, and then number 7, 8, and 9 are also without replacement. So only number 6 would be truly, the events would be independent of each other. Okay, so I'm going to stop the video there, and that should answer all those questions.